Hello everyone, welcome back. Now Liwei Ji, he is a postdoctoral researcher at Rochester Institute of Technology, and he is actively contributing to the CarpetX. Today we will be hearing subcycling feature he implements in CarpetX. Liwei, you can take it from here. Thank you.
Thank you, Bill. Hi, everyone. I'm Liwei. I'm from IT. Uh, yeah, today I'm going to talk about the subcycling integration within the CarpetX driver. Uh, so, um, so for the past two talks, Roland and Eric already spent some time talk about the CarpetX, so I will skip this slide. So let's just go straight into the subcycling uh, implementation. So here again is a plot compare subcycling and non-subcycling. Um, the left one is the subcycling, the right is non-subcycling, and the x-axis the spatial direction, and the y-axis is the time direction. And without subcycling, we are stepping forward with all the levels together, say for 1, 2, 3, 4. And if we're using subcycling, because of the different resolution on different level, we can take different size of time step for different levels. So as you can see, at the beginning, you can take a step on all three levels. The first iteration, like for the coarse one, the second coarse one, and the fine one. And for the second iteration, because only the finest one will need to make the second iteration such that it can catch to the second course level, and for the iteration three, because then both the fine and the second the fine one can make iteration three, and only the finest one for the iteration four, and they catch up with each other again and you can iterate the whole process. Um, by doing this, you can reduce some of the right-hand side calculation because you don't need to uh, iterate all the levels. Yeah, for the small time step. Sorry, I want to mention that please stop me if you have any questions or you have any comment. That will be appreciated. Um, so um, so again, so if we are looking at well, if we are say trying to solve Einstein equation and we write into a PD uh, a PD form of Einstein equation, and we initialize the data initial data in the initial time slice and move the time slice forward with time integrations method, say RK method. So we can generally consider ordinary differential equation, and we prepare some initial data, and we want to evolve this initial data to fill in the rest um, of the solution in time direction. So and here's a very description of the RK4 method. So Yn is the beginning of the current time step, and the Yn plus 1 is the finish of the current time step. And at the beginning, we have initial data Yn, and somehow we prepare the intermediate, I would call intermediate right-hand side, the case. Then somehow after that, then we can just using this expression to get the expression of the y at the final time of the current time step. So here's the expression of the case of intermediate right-hand side. So as you can see, it depends on the K1, depend on the initial stage, which is Yn, and K2 depend on the substage. We call it Yn plus h over 2 times K1. So we call this stage, intermediate stage, capital Y, Y2, and similar for basically we at beginning with this expression, then we can prepare the whole expression of the Yn plus 1. So here we just came up a new name with capital Y to represent the intermediate stage of the arcane method. So here we have two type of values. The K are intermediate right-hand side, and the capital Y are intermediate stage. They are related through some kind of linear combination, if you can see through the expression definition of capital Y on K's. Yeah, that's the arcane method. So first I want to talk about the subcycling method, which is implemented in Carpet. So here again, the x-axis is the spatial direction, and the y-axis is the time direction, and this black dot are basically the boundary between the coarse level and the fine level. The left is the coarse level, and the right is fine level. And as you can see, that it requires two sub-steps from the fine side to catch up with the coarse level. So in Carpet, yeah, then if we look at the arcane method, so at the beginning, we first do a time integration with the coarse level. So then after that, we do the iteration on the fine level. So, but when you prepare this intermediate right-hand side, basically the case, you need to evaluate this f function. And in the PDE case, this f function will be contain the derivatives, spatial derivative of the state factor. So then if you look at the boundary point of the fine level, then it's missing some information from its neighbor of its coarse side, because you don't have a fine sampling, a fine stem cell in the coarse region. So you need to come up a way to somehow prepare the ghost of the fine such that this f function can be evaluated, and then you can prepare the case, and you can move forward from the fine side. So here, so these black dot are actually, sorry. So this even fine are the RK substage. So the two state time step are the sequence. So it only two sub-step for the fine levels, and the black one are the boundary point of the fine level, and this circle, one circle represent one goal size of the one goals point, one size of the goals points that are required to the fine difference you're using. So one point. So suppose that we have two goals point in your simulation, then basically this 1 point represent two goals point. And if you have two, that basically double, and you have three, you have triple, and so on. So in Carpet, what we do is that so this is the very beginning, and we prolongate the first. We do a time integration to a time integral, sorry, to a time stepping in a coarse side, and then we do a spatial prolongation to fill in these circles using the coarse side data, and then after that you can you can using the RK method. And because of that, if you look at this point, because you don't have the information from the left side, so if you do this integration, then this point will be invalid, and only the three of that will be valid. And this is just the evaluation of K2, no, Y2. So then if keep evaluate this F function, then basically the more and more point become invalid because of the information you don't have from the left side. So in order to make the Y4 valid at the boundary of the fine level, you at least have 4 times size of the ghost points in order to make you have a valid Y4 for the finest level boundary. So then but we only make the first substep for the fine level. So in order to make the second substep, what we do is that we do a time interpolation from the core side of grade to fill in, to basically update these circles again to fill in, because you already have data, you already evolved the cost level, and you can do a time interpolation to fill in the blue circles. Then you can repeat the process we just talked about, and such that the fine level can catch up with the finish the second substep and catch up with the core level, course level. After that, we do a restriction such that to update the course level, which overlap with the current fine level, because we believe that the fine level has much accurate data compared to the course level. So that's basically what we did in the CarpetX case. But as you can see, we have the one of the issue that we have really large, which we call the buffer region, which is 4 times size of Gaussian. And imagine that you are trying to using more and more processes, and then there will be more and more more and more processes, such that the interior number of point will decrease, and in the end, the ratio between the buffer zone and the interior point will be really large, and it will cause the bottleneck for if you want to scale the code if we're using this method. So then we are basically trying to see if we can solve this problem by get rid of point, then which is very similar to the interprocess bound. Oh, how about now?
Sorry, you can continue now. Yeah.
Oh, okay. Yeah, sorry, my connection is also not very stable. I'm sorry about that. Okay, then so basically we want to see if we can get rid of the 3 extra gauge size. So we only want to keep 1 layer of gauge point, but also have a high order accuracy when we do subcycling. So if we look at this, when we evaluate this K, if you want to have valid boundary a case, all you need is you just only need 1 layer of Y's, which will be used to evaluate the case for the next case you want to evaluate. So somehow we can fill in this layer. Of course, differently we can do that. So Actually, this substage wise can be expressed as a theta expansion in this direction around Yn, and the expression is the following. If we can Yn, we know we already have that. If we can find a way somehow to fill in this time derivative of y's, evaluate at this Yn, then we can fill in this capital Y's by using this expression. Then the next question will, how can we prepare this time derivative of Y's with the information of the cos side? So luckily we have this dense output. Basically what it means that if you already make a time make a time step in the cos side, then you basically have the whole information of this function up to first order accurate. So you have an expression of this y, and also you have an expression of the time derivative of the y. We can just evaluate this function at the Yn, then we can use these values to fill in that such that we have the y's at the first cos size. Then we can only capture one there of the ghost points. So here's again the same plot, but we get rid of the extra three ghost size points. So that's again repeat the process more with more details. So first we made a time. First we make a time step on the cos side, which then we will have Yn is the initial, and k's are basically the case that you have the sub right hand side that you produced during the time stepping of the cos side. So here L minus 1 represents the cos side, L is that, then L represents the level of the fine side. So first we do a time stepping on the cos side, then after that we prolongate all these variables Yn and all the k's to the ghost point of the fine side. We do a prolongation such that the ghost point of the fine side of the fine level will have a copy of all these variables. Then we can use the dense output by use this time dense output such that we can translate this Yn and the k's into the Yn and also the time derivatives of y's in this ghost points. And after that, as long as we already have the y and the capital or the time derivative of y's, then we can represent this capital Y's, which is the substage of the arcane method, which is required to step forward using the arcane method. And as you can see, this y are the y's now corresponded to the fine level of the one level of the state vector. Then after we already calculate the capital Y's, then it's quite trivial to evaluate the k on the fine side, which will be used to update the state vector on the fine side. So that's, I think that's basically the algorithm that we implemented within the subcycling in CarpetX. So again, let's compare the Carpet and the CarpetX. So here the black point represented the interior point, and the circles are represented the ghost zones or buffer zones as you can see, by using the new method, we can get rid of the 3 copies of the goal size points by using the new method. And we expect that it can help with the scaling of the scaling performance of the code. Okay, so as a test, so we implemented the algorithm we just described within the CarpetX, and the first test we do a scale wave, very simple setup, scale wave simulation, and so the upper panel is the simulation with uniform time stepping. Basically, we turn off subcycling, and as you can see that they are converge at the first order because we are using first order final method. They converge at the order of a first order. They are first order convergent with the non-subcycling case. It just as a reference. So in the subcycling case, we turn on subcycling and doing the simulation, same simulation, and we observe comparable behavior is also first order convergence for the scalar wave phase. So that's a very simple test. And then next, we want to go to a more physical setup, which is a BBH simulation. So before we do already have a say for C, which will exist a long time ago, which works already, but we want to because we want to compare the Carpet and the CarpetX. So what we do is that we using a code generator to generate the same right-hand side, the exact same right-hand side for Carpet and the CarpetX. Then we compare the speed between these two. So we remove the difference in the right-hand side implementation and only compare the difference which coming out from the rest of difference between Carpet and CarpetX. So we use this new code generator called Generado, and then now it supports both CarpetX and Carpet, and also 2 other code, and can be the right hand side can be generated using this code generator. And now we already use this for CarpetX. We already use this code generator to generate two version of Save4C. Save4Cow is just a re-implementation of the Save4C song, which exists in the space-time repo already. But Save4Cow GPU is made a few modifications, such that it's more efficient running on GPUs. Then we also generate a native wild scalar. Basically calculate the well scalars compared to just Y scalar 4, which is porting from the Carpet. So of this, here's an example of how this code generator looks like. So here's a expression of the momentum constraint of Einstein's equation. So in the code generator, it looks like this. So it's based on the tensor package called XX. So it's using the convention that without minuses, up indices, with a minuses, down indices, and this underscore is basically the mathematical convention that this is free indices. And so as you can see this is the original expression, and that's how this is the expression of the equation that you saw in the code generate how you express this equation in the code generate language. So and if you have a up and a down indices which have the same index, then they will basically contract, and they will translate into the sum of the So yeah, basic contraction. So that's how the code looks like when they the code translate into the C functions and yeah. So with that, we implement we re-implement the stable system and using the code generator, and we run both the copied and CarpetX version of that stable C implementation. And first, we check the accuracy. So this is with the subcycling turned on, and this is very simple setup, which is Q equals 1 and non-spinning binary black hole. And yeah, here we compare 3 different resolution. Yeah, from black, orange, and the blue is from low to high resolution, 3 different resolutions. And we also look at the convergence order. So the black is low resolution, and yeah, the black is the difference between low and high resolution, and the orange is the difference between medium and high resolution, and the blue one is the rescale of the orange one. Assume that is first order convergent. So as you can see that the blue and the black one agrees pretty well, and yeah, which means that we have first order convergent with the subcycling implementation. And for the correctness, we also compare to a different code, which is LAZEV that we have in at IIT. We compare the amplitude and the phase between these two code, and I believe that difference between these two code is more than 0.1% in both the phase and the amplitude. Okay, then because we talk about we are expecting that the new subcycling implementation should have better scaling performance. So we did a scaling test for Carpet and CarpetX with subcycling. So this the yellow one is the Carpet one, and the blue and black are Carpet and CarpetX. Blue is running on CPU and black is running on GPU. So both of Carpet and CarpetX have this exact same right-hand side expression. So there's no difference coming from the right-hand side implementation. So as you can see that by using the new, well, there's maybe the driver is different. So I can just say that we see a difference both on the absolute speed. I think it's almost twice faster if we're using CarpetX version of the code, and it also scale better compared to the Carpet version of subcycle with the subcycling implementation. So almost twice speed up. And by running that on GPU, you can have extra 15 times speed up for 4 node. And I believe this is 7 times faster for the 64 node case. That's strong scaling. And if we look at the weak scaling of the 3 different setup again, they perform they have similar performance. So both of them are close to 80% at the 64 nodes of the for the same simulation setup. Yeah, conclusion. So we have implemented a new subcycling algorithm with the CarpetX driver, and we achieve theoretical higher order, which is first order. But we see first order convergence in our simulation, but theoretically the Carpet one only have second order convergence because of when we interpolate in the median median time step from the cost side. And we also have better speed and scaling performance on CPU, and also that the current setup is GPU, yeah, GPU accelerated. Okay, I think yeah. Before I stop, I want to mention. Oh wait, first that's do we have any questions before I talk? Yeah, before I go to the next part.
You can continue, Liwei. There is no question as far as I see.
Okay, very good, very good. Ooh. Sorry. I have 10 more minutes, right?
Yes.
Okay, very good. So next part I want to talk about is how you can use the subcycling integration. So I made a small repo to describe how to use that. So first of all, right now, this only existing on a different branch, and we are trying to merge that to the main branch of CarpetX. There are pull requests, maybe a few that will coming, but we are trying to do that. But at the moment, if we are trying to do it now, you have to use a different branch of CarpetX and add two parameter in your path file. Well, if you already have a CarpetX song and you want to turn on the subcycling for your CarpetX song. So first, the first step is that you need to add more grid functions which store the old state and the K1, K2, K3, K4 for your state factor. Yeah, you will need 5 more state factors in your interface.ccl. And step 2 will be that for the non-evolution variable, you cannot call sync anymore because you might pull in the wrong data from time step. So you have to replace those if it's a non-evolution variable, and if only a pairwise operation, then you should use loop all instead of loop int plus sync. That's step 2, and we can skip step 3 for a moment. And I think after step 1 and step 2, it just for a really simple case, like say for C, then it just start working. But if it's hydro, then you need to think really carefully. If you have to think of any variable that you have, so we can, if you have that, we can discuss if you really complicated schedule function. And another tip is that if you are running on GPU, please use one OpenMP per GPU because some of the SOM does not support multiple OpenMP per GPU for now. And please turn off the tiling and yeah, it will cause a lot of problem if you don't do that. So here's a list of SOMs that's already compatible with the subcycling. Let's say for C in the different branch, and the other two SOMs which are basic a reimplementation of say for C, yeah, are also compatible with subcycling. So for AstraX, we also have a branch called refinement AC, which is compatible with subcycling. Here we only have one so-called GPU Renaissance, which write natively from beginning. But I hoping that this will become longer and longer. So for the example that I showed during the presentation, that I have a example profile list here, so you can take a look if you want to try it out. Yeah. Okay, I will stop here. Thank you. Thank you for your attention.
Thank you much. Thank you very much, Liwei, for your very nice talk and tutorial. Now we will have questions if there are any.